Hey guys, the last section of this review unit is the idea behind graphing. So we're going to talk about what you need to include in a graph to make it a valid and strong graph. We're going to talk about how to know where to place certain items, and we're going to talk about something really important called the line of best fit. And I know a lot of this is stuff that you've learned in previous years, so this should be a relatively quick review. So every graph needs three titles: the main title, the x-axis, and the y-axis. A lot of times in class, I'm not going to give you the information of which item goes on which axis, so you are going to have to determine that on your own. And I'm going to give you a couple hints on how to do that. Okay? In addition to the three titles, you need to have labels on each axis with the units given, and then the line of best fit, which we're going to talk about last. So in this graph shown, we have the main title, which is human population growth. There does not need to be units there because it is just a title describing what we're looking at in the graph. If you're making a lab report, you may be making multiple graphs, so you need to tell me which graph is which. The second one is the x-axis. Down here it's kind of hard to read, so I'm going to rewrite it. They simply title this axis with the word year. Now, year is already a unit of measurement in itself, so a different way we could have done this is time, and we could put year in parentheses next to it. Okay, so that's one way we could do this. On the y-axis, we have a second title, which is population. And they didn't use parentheses to label the unit, but they did label the unit. So here I'm going to write population, and then I'm going to label the unit billions of people. So this graph gives us the population growth in terms of billions of people over the course of time. Now, what you need to pay attention to, the x-axis is the independent variable. That is the one that's going to change no matter what. It is going to increase at a constant rate, it's going to decrease at a constant rate. It is the one that we are not adjusting as scientists, we are simply measuring. So time is very often the independent variable because time continues going on, and we only measure it in terms of seconds, minutes, or years. The y-axis is the dependent variable. This is the variable that ends up changing. This is the one that we are measuring as the outcome of our experiment. So since this graph is human population growth, our independent variable is time. As time goes on, what happens to our population? So our dependent variable is population. Now we're going to see a lot of examples of this. If we were to say, finish a science experiment that has to do with the amount of sunlight given to a plant and asking how it affects the plant's growth. We have two variables, the sunlight provided to the plant and the growth of the plant. The sunlight is the independent variable. That's the one that we are controlling, the one that we as scientists are going to manipulate ourselves. So I can decide to give a plant 5 hours of sunlight. I can decide to give a plant no sunlight and put it in a cupboard somewhere. But the dependent variable would be the growth of that plant. Okay, another example, if we were to measure rainfall over the course of a month, the independent variable is the day of the month. I determine when I'm going to make those measurements. The dependent variable is the rain that falls. I'm not necessarily controlling it, but it is an outcome of this experiment. Okay, so you always have to ask yourself, what am I controlling as a scientist, and what am I measuring as the outcome? The one you control is the independent variable. The one you measure is the dependent variable. In addition to those 5 things, main title, x-axis title, y-axis title, units on the x-axis, and units on the y-axis, you also have to include a line of best fit. So the line of best fit is really important because it not only allows us to predict future data sets based on the trends seen in the graph, but it also allows us to predict data for information that we may not already know. So if I look at the graph on the top to the right, this is a line graph. It does not have labels, so it's not necessarily a good graph as an example, but I wanted you to see a normal linear relationship. So this is what you may be used to drawing. This item or this data point over here is considered an outlier. We are not using it in terms of our line of best fit because it is so off the trend that that was just a fluke measurement. It's something that maybe was measured incorrectly, maybe there was a variable that we didn't account for that may have changed that data point, but we're just going to pretend it's not there. I like drawing these types of lines of best fit with a clear ruler because I can lay the ruler down, I can count the number of data points above the line, and then I can count the number of data points below the line, and you're always going to try to make them as equal as possible. You want the line to be as close to or touching as many points as it can be. But lines of best fit are not always linear. This bottom graph, this is a reaction rate of a chemical reaction. As time goes on, the rate slows down exponentially. As time goes on, the rate slows down exponentially because maybe it runs out of stuff to react with. You have a limited reaction, only certain numbers of chemicals are present. So here we have a high reaction rate. It is going pretty fast to begin with and then slows down over time. Now this is a very distinct curved line. The data follows a very distinct curved path. So if you were to draw a linear line of best fit here, so hypothetically like that, I would probably take a point off simply because it doesn't match the actual data set. Now, if there's a slight curve to the data and you draw a straight line, I can understand that straight lines are easier to draw. So I'm not going to necessarily mark you off for that. But if it is a distinct curve, I expect to see a distinct curved line of best fit. So remember, lines of best fit can be linear, they can be curved, they can be increasing, they can be decreasing. You have to get as close as possible to as many points as possible to make it the best line of best fit possible. That was a lot of possibles. So what we're going to be doing with this in class, we're going to be practicing making some graphs. I'm going to give you data. I'm going to allow you to determine what is the independent variable, what is the dependent variable, which one goes on the x-axis, which one goes on the y-axis, and I'm going to have you practice plotting the data. In addition, we're going to be completing an in-class lab that is going to have to use this skill in creating graphs for your lab report. So you will be showing the data in terms of graphs during your lab report. So we're going to be working with this, we're going to be practicing with this. It was just a quick review of titles, units, and lines of best fit.